Let me first for inviting me for this mini course. This is the first time I'm giving some mini course, so if I'm stuck somewhere or if there's something, please point out. If I'm speaking a bit lightly, please tell me because sometimes my tone goes down and I didn't realize. Okay, so then of this mini course that I'm going to give this 4 lectures will be, of course, it will be on foliations, and it will be divided into real and holomorphic part. Since it's a CR geometry, people are from complex analysis background. I will come to holomorphic foliations, but that will be the last 2 lectures. But even the first 2 lectures, which are on real foliation, all these things, all these results and observations, we can just go forward and take them to holomorphic case as well. But for holomorphic case, we will only see those results or those observations which are not there for the real ones. Okay, so I said this for word foliation a lot. Let me now tell you what is a foliation. So a foliation, intuitively speaking, it's a decomposition. So we have a manifold. A foliation is a decomposition of this manifold into submanifolds, submanifolds of fixed dimension, let's say k, and what this decomposition looks like. Locally, it looks like this. The pages of this book. So it's these submanifolds are stacked up on each other. This is the local description of a foliation. Globally, it can be very wide. That's why I said submanifolds, because they are not nice submanifolds. They are not embedded submanifolds all the time. They are they are known to be immersed ones. They can be embedded, but that's just a problem to find out when and how many of those submanifolds are those manifolds. Okay, so I gave you a intuitive definition. Let me give you a simple example. So just by the intuition, you can see very trivial sort of example of a foliation. You look at Rn, and you write it as Rk Cartesian code Rn minus k. So let's say this is Rk and this is Rn minus k. Now you partition this into this parallel coordinate planes. This is an example of a foliation, k-dimension foliation, because these objects, these submanifolds that I'm saying, these are called as the leaves of the foliation, and the dimension of these leaves of the submanifolds is the dimension of the foliation. Now, like, why do we need these foliations and all? So, what we are doing when we are having a foliation, we are partitioning this manifold into lesser dimension submanifolds. So sometimes, in order to study some geometric properties of the manifolds, it is easy to study some geometric properties of the submanifolds, which sometimes is easier to understand because they are of less dimension, and they give some restriction or some obstruction or some results about the global manifold. And we will see along the way how we are able to do that, because these objects, this foliation, locally or sometimes globally, they are related to various important objects in geometry. Let's say vector fields, one forms, and also submersions and all. So there are many objects that are related with foliations, mostly locally, but and through which we can study the properties of manifolds using some properties of these leaves or these submanifolds. Now, giving you some historical background. Actually, this theory is not very old one. It's only started in 1900s or something, and in fact, it started in the proper study started around 1930s on the work of Reeve. And so how he started working on this. So what happened was Hope, actually his work was around 1940s. Hope asked this question in 1930s. So he was looking for some sort of, he was working on S3. So it's a sphere on in R4. So he was looking for some sort of vector field, completely integrable vector field, which was orthogonal to its irrotational, which in foliation terms, he was asking whether there exists a two-dimensional foliation on S3. So this was the question in foliation term that Hope was asked, how Hope was looking for, which was actually answered by Reeve in 1940s, and he gave an explicit example. So although it's a particular example on S3, but it turns out to be quite an important one.
The dimension of the leaves, how do you refer to the dimension of the foliation? The dimension of the leaves or the transpose?
No, the dimension of the leaves. The dimension of the transpose would be the codimension. So yeah, we look at this example of the Reeve foliation after a while.
What additional property are the leaves supposed to satisfy?
So at this moment, we are just looking for some any foliation, because if we go one step, like if we look at S2, the Riemann sphere, there are no foliation of one dimension. So maybe that sort of motivates, like whether we have codimension one foliation on S3. Smooth foliation.
Yeah.
Smooth. Yeah, I'll be working with all smooth. We can have this foliation as less regularity.
Same thing, you have singular foliation of S.
Yeah, okay.
That's
in
what we are
that
thinking
regular.
of.
Okay. Yeah.
Just a longitude. Very
Yeah,
good.
yeah.
Yes.
So I think
Right now, I'm not going into singularities. We will go into singularities, but when I go to holomorphic case, there these singular foliations are more common, and we have some more structure using some SCV results. We have some nice, nice we have some nice description of singular foliation in terms of holomorphic objects like vector fields and all. And this foliation theory, it does intersect with various branches of mathematics like algebraic geometry, differential geometry, ergodic theory, dynamical system, and topology. So people working in different areas do work on this theory, but with different perspectives.
what was the answer maybe?
So he gave a specific foliation. I'll give you the construction of the foliation later. I'm just giving you what happened. Now, okay. So Reeve, he gave a example of smooth foliation. Then around 1956, actually, I call it F figure. He showed that there does not exist real analytic two-dimensional foliation. So he said, like, there are smooth foliations, but there are no real analytic ones. And after this, few years later on, Novikov proved that this foliation, this Reeve foliation, is actually very important, because although this is just one example of a foliation on S3, but he proved that if you take any other two-dimensional foliation of S3, it will look like Reeve foliation. So why Reeve foliation is important? Because there is this object, this submanifold, which I am calling leaf. Only one leaf is very nice. It's a compact submanifold, and all other leaves are, yeah, less nice, but they are kind of accumulating on that compact leaf. I'll give you the picture. And also, okay, just before I move forward, not only on S3, but any connected, simply connected three-dimensional manifold, this property holds. Right? So if you take any two-dimensional position on that manifold, smooth position, it will look like ring position. It has a compact leaf and all other leaves which are copies of R2 and accumulating on this compact leaf. All right. After that, there's been many important results which have been done about position. I won't go into all these details. I'll just start with the. If you don't understand many things here about what I'm saying, it's okay. I'm just giving some historical. I'll start with the proper definition of foliation and then give you some explicit examples, some easy ones, and then some nice. Okay. So let me give you the proper definition. So when I gave you intuitive definition, it was very easy to digest. But now this definition, it might take some time to see what this definition, how is this definition related to what I gave you this intuitive definition. But we'll see. Let M be a smooth manifold. Smooth manifold of dimension N. A smooth foliation present a foliation with this. Smooth foliation is an atlas, the smooth atlas. There are these charts UI, index, which is maximal in the sense I'm saying a position is a atlas, the maximal atlas of charts. But what should this atlas satisfy? What property should this atlas satisfy? First is that every, okay, I can do this with anything. It's not it's not like it's not a very important property in some sense. You can write Ti of Ui as let's say you take any coordinate chart P and U. I can write this as U1 cross U2, which is subset of. So here U1 and U2 are open disk in Rk and Rn minus k. This I can always do. I know that if it's a coordinate chart, it's a diffeomorphism in Rn. I can always find this U, and I can write it as Cartesian product. I can write it as Cartesian product of lesser domains. Yeah. So first of all, I'm taking a coordinate chart which looks like this product, which has this product structure. Now, this is the important property which actually makes it a foliation. This we can always do with all coordinate charts. It says that if two coordinate charts, two of these coordinate charts intersect, then condition that satisfy the transition that, I mean, let's say is P and psi compose psi inverse. This I can write now that psi of the intersection is this is in this Cartesian coordinate. So I have these two coordinates. One is x is coming from RK.
Now it's fine.
So yeah, so what it satisfied. So I can write it as like this. These transition maps are maps from Rn domains in Rn to Rn. Now the main important part is that this last n minus k coordinates, they are independent of the first k variables. Now this might look like something weird. Where is the foliation coming in? Now, okay, can these are actually coordinate charts. So, what? I couldn't.
Is this final satisfied for all I smaller equals to capital?
Yeah.
So I guess this question is, since you call your atlas UI phi, but the first point is phi u.
Yeah.
His point is there's I, and also this should be true for all I.
And maybe then in that case I have to write them. And
in particular, I guess the parameter k remains fixed for all I.
yeah. So this decomposition of like the way we are writing this image of the charts, this remains same because we are looking at k dimension foliation. This we can do with like if I take a image of U, this is in Rn. Let's say this is the image. I can just take some domain like this and put it back, and I get another domain U tilde. Now I can take my domain to be U tilde. So this image is looking like this. This is nothing like to do with the foliation. Okay. This doesn't give us foliation. What gives us this partition is this condition. And how is this giving us this partition? Let's look at this picture. So these are maps from. So this is a map from Rn to Rn. These are components of. Okay, this belongs to. So H is a map into Rk, and G is a map into Rn minus k. Yeah, this is the number of components of H and G. So let's look at these two coordinate chart. U1 and U2. Now I can map this to this Cartesian, to these nice domains, product domains, and so this is P of U1. Now what I can do, I can take this nice set of foliation, the position like it. I take this position here. This is k-dimensional position of this domain. But since phi is a decomorphism, I can pull it back and I get this partition on U1. Right? And same thing I can do for U2. And I get another partition for U2. But this condition tells us that in the intersection, these partitions, these submanifolds, these inverse images of these curves or coordinate chart, these coincide. So they actually coincide and give us some global object. Here I can extend this and I get this. So and doing this for each coordinate chart, we get these global objects. So you can start with one of these and then extend along all these coordinate charts, and this is what roughly, let's say, the definition of leaf of this foliation. These are the objects that will partition this manifold. And okay, so these objects, local objects, which are EI, let's say here in this case, P1 inverse of. So here it was W1, and here it was W2 in this direction. So it was W1 times point Q. These are called as plaques of the foliation. Plaques are just the inverse images of these lines, these leaves of this particular domain. And patching them up actually gives us the leaf, the global objects. So these objects are quite nice, as from what we can see. These are just inverse images of nice complex. These are nice coordinate lines. Yeah, this is just a copy of RK, not a copy of RK, WK, W1, and we are taking it under a diffeomorphism. So it's a nice manifold here. But when we patch these up and we get this global object, it might not remain like nice like this. It might, after the coming back, it might just come back again and again and again in the same chart. So it's the global study of these objects that becomes like, that's the global study, which is a bit difficult and important, because the local study, there is nothing to study in these charts. It's just parallel lines, parallel pages. It's the global study, how these leaves are situated inside the manifold. If they are nice, then they are embedded closed. If they are immersed, how they are situated. And we will look at how they are situated in this manifold, or how they cannot be contained in manifolds. That's another case. Like in the next time when I discuss especially about these leaves, we'll see that what objects cannot be leaves of foliations. Just because of the behavior of these leaves in a manifold, we can see what kind of submanifolds cannot be leaves of any foliation. So is the definition of foliation clear? Okay, just some terminology. These charts UI PI are called as the foliation chart. And yeah, as I already said, these are called as plaques of foliation. Proper definition of leaf of foliation. I just gave you a heuristic definition of how to get this leaf and why it is a submanifold. Part of plaques. This you got what, right? What a plaque is? A plaque is just an inverse image of these lines, these objects, these ones. This parallel, this you can say parallel open this in RK.
Sorry, what did you say? That was the leaves.
No, these are leaves of this coordinate chart, but when we take them here in open set,
They are.
yeah. No, here when we just consider this one part on our open set, this is a plate.
Okay.
And kind
It's
of
part of it.
gluing them up, the object that we get after gluing up, that we call as leaf. And just give a proper definition of what this gluing up means. So a part of plates of the position, finite sequence. Yeah.
That's feeling.
Okay. Yeah.
Yeah.
This V1, it doesn't look like.
Oh, P1 here.
Oh, I changed my.
It's fine.
Here I changed my. This was not. I changed my notation somewhere.
Okay, back of the chart.
Yeah, so I mean, can just say that if phi, comma u, c, comma d are in that atlas.
Yeah, yeah.
That's the answer. Yeah, because it'll be kind of nuts to write phi I, phi j, and then you have a W1 and a W2. So yeah.
J's attached to them.
Yes.
Yeah.
So
Basically several complex variables by this time. I think it's X already.
Yeah, they are telling this to be the chart, this atlas to be the foliation.
Right. What I was asking is there a notation F already there for the atlas?
Yeah, yes. So although we don't think of foliation as atlas, we are kind of thinking as a
Yeah, I
partition,
know.
but yeah, this definition does just say that it's a atlas and it's a definition. Okay, so yeah, a path of plates is a finite sequence. Plates alpha 1 to alpha r. Okay. Alpha I intersection alpha I plus 1 is right. What a path of plates is? So here, let's say I'm in a two-dimensional position. So here is one plate, and here is another one. And kind of take this finitely valued. The adjacent ones kind of intersect. This is called as a path of plates. Now, just before so here, in one coordinate chart, two plates are either same or they are disjoint, just by the definition. These are disjoint ones. This is the partition of like parallel disjoint, parallel disk, and so the three images will again be distinct, completely disjoint. So in one coordinate chart, no two plates intersect on opposite. They are either equal or they are disjoint. But it's the plane of this adjacent coordinate charts in which they get intersect. So this is how I'm getting. So here was some coordinate chart. And here again there was some coordinate chart. So I'm taking plates of these charts. This is what is called as a path of plates. So we define our equivalence relation. Define equivalence the manifold M. So we are defining the equivalence relation on the manifold. And only if there exists a path of plates R that is an alpha 1 and U is an alpha r. So 2 points are identified or related if we can move from one point to another one using a finitely many plates. This is how I'm giving this plate, and this actually an equivalence relation. It's easy to check. I think it's quite easy. And the so the partition, so this under this equivalence, the equivalence class under this relation are actually the leaves of the formation. So this equivalence classes are these global objects that we are getting. So is the definition clear? If you have any question, please ask. Because when I go to examples.
So in that in those two atlases, what condition among A and B ensures that these sort of don't intersect and sort of overlap?
Conditions of A and B, what are A and B?
Foliation definition. Yeah. What condition ensures that if you take one line from M and it's not
Yeah, because if you take, let's say if you take this slice, what is this slice? This is given by x k plus 1. Since I'm writing it as xy, r k plus r n minus k. So this slice is nothing but this y1 equal to constant. Okay, let's just say yi from 1 to n minus k. This is correct. This slice is given by this last n minus k coordinates as constant. Now, if what I'm saying is that this last n minus k coordinates, they only depend on these n minus k coordinates. Now, on this slice, they are constant. So, this is actually constant on this slice. So, when we come here, so let's say this is the intersection part. When we take the image of this slice in the intersection through the transition map here, what happens is the last n minus k coordinates are constant. So they are mapping these curves to these curves. And this is how we are getting this patching up. It's clear?
Only these are the horizontal lines.
Horizontal lines is k dimensional. Is
So if this were a two-dimensional picture, then it will be exactly horizontal lines.
Yeah.
In general, we have k minus 1 dimensional discs.
k dimensional.
So by disk, we mean in your definition above, you said that each W1 and W2 is an open disk. You mean a ball, is it? Or you mean a box?
No, both.
No.
That's why the second component is a function. What is the function of one?
So these are n minus k number of variables.
So the definition is actually meant to include the fact that if you were in two dimensions, a horizontal line, if you're viewing it under a transition function, you go to another horizontal line.
Let's come to examples. Again, the first example was I give again come to this nice one and take u r n minus k the open sets connect to open sets. Cartesian product. This is a natural k-dimensional foliation, where the leaves are just this opening of U. Leaves of so this is one foliation. When I'm looking, trying to see these objects as leaves, there is another one. Then we can think of these objects as leaves. Then we get n minus k dimensional foliation. It's not like a requirement that we need to assume that these are open sets in Rn. What we can do, we can just take U and V to be manifolds of dimension, let's say U and V are smooth manifolds of dimension k and n minus k, and also this one. And also this one. The coordinate, the position chart will be kind of this Cartesian product of coordinate charts of this. It's very easy to see the foliation before coordinate. Now, using this remark, let me give you another example. It's not like the non-trivial example here, but I'll construct non-trivial example like starting with this. So let's take U and V as well. So our circle. So what is V is S1 process, it's a torus. Now, what the position here would be if we are think of it depends like which S1 we are to think of as this. One way is that these are the leaves of these circles kind of foliate this torus. And another one, if we think of as the how to say meridian.
These are the
These are the meridians. What are the so other one would be to think that so we can take these circles as well to foliate our torus. So this is an example of a foliation, a one-dimensional foliation on torus. Now, again, these are very nice examples of foliation where each leaf is a nice submanifold of the global manifold. Now we want to see that because when I was giving the definition of foliation, I told you that these leaves they are not necessarily nice submanifolds, embedded ones. But until now, the example shows that they are. Now let's see an example where they are actually not. And I'll start with I'll give you an example on torus only. Now there is another way of looking at these foliations, these two foliations, and this is
just by your definition. Yeah, a leaf is an inverse submanifold, right? Or is that
so
also too strong statement?
So that's the most. That's the least we can say.
Okay, so at least that much
yeah,
is the
immersion
almost by
part,
definition, right? Because you have these box charts, and each leaf is really a slice.
Yeah. Okay. Maybe we can say a bit stronger. It will be 1-1 immersion. 1-1 immersion. It won't intersect. Self-intersecting things.
Right. Not even self.
Yeah. So, but immersion is the most that we can say. Now, let me tell you another way of looking at this foliation. We start with R2. And we take the partition or the foliation of R2 by these horizontal lines, horizontal copies of R. Now, you know what is torus? This we know Z to X on R2, and under this action, what we get is the torus. Now, this foliation, this partition of R2, actually induce a foliation on torus. Although it's because of this is being invariant under this vertical translation and also horizontal translation as well. So, what this foliation is on the torus? That's one thing. So what happens when we are identifying these things? We can just think of this square, and what happens is how we get torus. We are identifying this curve with this, and this one with this one. So a leaf which here is our leaf passing through this. What will be the induced leaf on torus? So here is a point. We start along this vertical horizontal direction, and we end up here. Now this point is again identified with this original point. So in the torus, this we can think of as this is the induced leaf, and every horizontal line will give us a circle like this on the torus. And again, in a similar way, instead of taking these horizontal lines, we can take vertical lines. And this time, what we get is the other position of torus. It's the position by these horizontal circles. Now, this is like two special cases of partition of R2. Now, instead of taking this horizontal or vertical, what if we take some other partition of R2 with some different slope of real lines? If we take different slope, then we get a different position, and depending on this slope, we get some quite complicated foliations on torus. Let's, for example, we take a partition of this R2 with lines of slope alpha. The slope is alpha. Okay, so what happens? Now let's look at this square. You know, these sides are identified. We start with one leaf. Let's say it starts from here, and this is how it goes. It intersects here, and then the actual leaf goes on. But now here, this point is identified with this point. So we take the leaf that was passing through this, and we start with this. Now it intersects here, which is identified with this point. Then we take this point, and we keep going on like this. But on torus, when we see what is happening, is when so when we started with the point here, we go around, we came at some other point, then we again went back, and we are overlapping, we are kind of spiraling around this hole, and this is going on. Now, depending on the slope, is the behavior of this leaf. I won't prove this. Let's keep it as an exercise. But it says if this slope is rational, then this process ends after some time. So after some finitely many times, we again start with the original point. So this loop ends, and each leaf is homeomorphic or decomorphic to S1. So again, if the slope is rational, we are again getting a partition of the torus through circles, but these circles are not like the simpler ones that we get before. They are kind of spiraling around this hole and then. But the other case, if alpha is irrational, and each leaf is a copy of R, this process never ends. It will keep going on, and in fact, is hence So this process that I told you, this spiraling around, if the slope is rational, this will keep going on, and the final image that we get of this after getting this spiral, this is dense on torus. So each submanifold we are getting that are partitioning this torus, this manifold, is dense in the manifold. So of course it's not an embedded submanifold; it's an immersed one.
So I can just put since your action is not by 2 pi z cross 2 pi z, but by z squared.
Yep.
I suppose you literally need if 2 pi upon alpha is rational. Right?
I guess that would, yeah, you are right. We need e to the power 2 pi alpha, and that should be irrational to get this denseness part.
So either 2 pi I alpha is in Q cross Q, or equivalently 2 pi upon alpha is rational. So in other words, 2 pi is a rational multiple.
And now let me give another example in which we get foliation, and then we will see that these are objects which actually define foliation locally. Seven questions, please ask.
This homomorphic of that which of the leaf is
If you go to
R,
it's about your
but it is still dense in
it keeps spiraling around. And now let's see another way of constructing foliation, and this is through submersions. So let F changing the dimension of M, because I'm taking two manifolds. The dimension of the manifold M is M, and capital N is the small n. So let F be a submersion. Smooth submersion. And so I claim that given a submersion, there is a foliation of the manifold of dimension is the foliation of M of dimension M minus N, and the leaves which are partitioning this manifold are nothing but fibers of this F, the inverse image of the components of the inverse image of this. Let's see how, I mean, of course, you can see the picture how this foliation, these fibers are partitioned, but let's write it in focus that foliation definition comes. By the way, I think everybody knows submersions, what submersions are. I'm already taking this differential geometry thing as a prerequisite for this thing, because I'm talking about vector fields and all without going into the details. So so locally a submersion actually looks like a projection. So we use that property. So from the local form of submersion, let P be the manifold M, and Q, which upon P, and there exist coordinates on both ends. There exist coordinate charts. Coordinate charts around P, side around F, around Q, such that yeah, such that so we can take this small enough so that the image of P goes into V. Yeah, so such that this P inverse I equals to F inverse of XY. This is nothing but Y, where XY is in, here I should be careful, or 1 minus N. XY, this is in Rn. M is of dimension M. So the image of Phi is in Rn. I write Rn as Rn minus N. So Cartesian with Rn. And we have coordinates. We can find this coordinate map such that locally it looks like this. This is nothing but the projection onto the second component. So phi. Okay. So these local forms actually defines the foliation chart. So these coordinate chart P, U, we can find it around each point, and these turns out to be the foliation chart. Now I can just take this atlas, of course, P and Q, and this is over like all points, and now what we need to calculate is the transition map condition. That's what we need to check to show that okay, these coordinate charts do indeed give us foliation. Let me quickly tell you how to see this. Okay, so we take two coordinate charts. Consider two coordinate chart. Coordinate chart. Let's say one, I'm taking this one. Such that U1 intersection U2 is known as taking to intersecting coordinate chart. Now I want what this coordinate map looks like. P to compose P1 inverse xy. I can write it as hxy and kxy. Of course, I can just write this. Write it like this. I need to show that this map K only depends on y. It's independent of the variable x. And to do that, we need to use this local form of submersions. Okay, so to do that, consider this map. Okay, to compose F inverse. So corresponding to each phi, I have a map. I have a coordinate chart. Psi 1 and I have V2 psi 2. The definition of submersion. These are on n. So I'm taking this map psi to compose F on P1 inverse. So this is on the. Here I have these two charts, U1 and U2. again here I have two charts, V1 and V2. I'm working in the intersection. Are these coordinate charts. So V1 inverse, I can write it as psi 2 with P2 inverse. This is just identity map. I write this as this. This is nothing but I'm just in between. I'm composing it with the identity map. But now taking this with this, and this is nothing. This is the transition map. So psi 2 composed with P2 inverse. This is HXY AXY. Because I wrote my transition map like this. No, not this. And from local definition of submersion, this is nothing but the projection of the second component. This is just K. Now let's one more time we consider the same map, but this time instead of having this identity map here, we'll add over here. We'll write it as psi 2 composed of plus and now if you look at this map, this is the projection of two second components. This becomes this this one. So we showed that this term was equal to the second component, this last n minus k component of the transition map, but this is also equal to this function, and this is independent of the first k value. So we showed that the transition map condition of this coordinate chart satisfies, and we indeed have a foliation on the manifold M of dimension n minus n, and these are actually from here we can see, because we are taking the coordinate chart as charts which are given by the definition of submersion. So the leaves or the plaques, they are in fact the fibers of this submersion. Okay, now let's go to the example of reef. Let's look at the reef foliation that I talked in the beginning. Let me tell you what the idea is. So the idea is that first we decompose our S3 into two solid torus. So we write S3 as union of two torus which share the boundary being the torus, and we foliate each solid torus separately. I mean, we take we take a foliation on the solid torus and we take the same foliation on each one, and we showed that this boundary, this torus being the boundary of this solid torus, which is being shared by these two solid torus, is again a leaf of the foliation that we are. Maybe too much information in one sentence. Okay, let's start looking at by here we have S3, and S3 is a unit for one radius sphere, let's say sphere. So it's square plus square plus set of points to satisfy this condition. Now we take two sets. Even we take points x in S3 such that both x1 square plus x2 square, this is less than equal to 1 by 2. Now the complement of this being mod x1 square plus mod x2 square strictly greater than 1. X1 square plus by 2. But we can take instead of strictly greater than equal to, so they are not disjoint, but the intersection is the actual torus. Now this set we can identify. We can also write it as like this. Instead of working with x1 and x2, it's x3 square plus x4 square less than equal to 1 by 2. Write this set as in terms of x3 and x2. Now, if you look closely, both these sets T1 and T2 they are solid torus. So, if you look at this both as x1, x2, this is a 1 by square root 2 radius disk. So this is a disk. In R2, this is a disk, right? And on each point of this disk, the corresponding x3 and x4. So if you fix x1, x2, in square plus square. So that so the R defined into this modulus.
See more
Yeah,
it would become cleaner and people would see the torus.
Yeah,
But anyway,
that's more,
fine, it's fine.
that is more.
For the
That's the
complex
way
analysis in
actually
the
I,
audience, yeah.
that's the way I saw the decomposition.
Yeah.
So if you take any point in this disk, the corresponding x3 and x4, they should satisfy this. 1 minus r. No, let me show S3. So corresponding to each point on this there is a S1, there is S1. So each Ti is decomposed to a solid torus. Let's say D closure. This is when is this or this is same as D2. Mod x y square less than equal to. This is a subset of R2. So both we get a decomposition of our S3 into two solid torus. Now we just need to foliate each of these torus by two-dimensional surface. Is the decomposition clear? Okay, now let's what we will do is be working with this. Not with this side, but this closure goes up. So as well. No, not right now. So consider this map F. This is defined by F of x1, x2. Let's say y1, y2. There are three components. These are three variables. This is defined as exponential of minus exponential minus r square times b to the power x3, where r square is load y. This is the map that I'm considering. You can check that this map F is a submation. So, being a submersion, this will induce a one-dimensional curve. So, this is three-dimensional, and this is one-dimensional. So, this will induce a two-dimensional foliation on. Right now, we can think of either as open or closed. Let's right now let's think of it as open list. So, it will give us a two-dimensional foliation of this D cross R, and the leaves are the level sets of F. Now we'll see what these level sets look like. So first of all, this is a positive map. This image of F, or even this deep closure, this is both are exponential maps. We'll see the level set of this map F for each one. So if say F, F inverse C, F, first case C is non-zero, or C is strictly positive. In that case, I can write, because my F is exponential of this plus y3. So F y equal to C, this means e to the power minus exponential 1 over 1 minus r square plus y3. This is C. So this constant is positive, so what I get is y3 is exponential of 1 over 1 minus r square plus log C. So the level set of C positive are the graphs of this map. And what is the graph of this map? This is kind of paraboloid. This looks like, if you look at in R2 right now, this is the y1 y2 plane. This is y3, and we are looking at on this line. So for each C, these leaves look like this. These will be the level sets of this map. And if then you get that R is 1. So this is equal only. So this means that this F inverse 0 is the set. Yeah, so this cylinder, the boundary, this is you get two kinds of leaves. One which are paraboloid, and what happens is along the boundary at infinite they are kind of accumulating on asymptotically.
This is opening, like your thing is opening down. I mean, your paraboloid is just getting a hole in it, and it becomes a cylinder.
That part is outside. That if we take this map F on the whole R3, then other leaves would look like this. But inside this, these are paraboloid. Yeah, they finish somewhere here. So they start with somewhere here, and then they, because if you think of it in R2, let's say we remove this variable.
No, I'm just thinking of C going to, as C goes to 0, C is your parameter, that's
Yeah.
fine.
So
As C goes to 0 on the curves.
yeah, okay, yes.
So it's opening. It's
Right.
opening.
As C goes to 0, as C goes to 0, these or these level sets they are going down, and they are kind of going towards this boundary. And again, from this last observation, this boundary is again is a level curve of this map from the point 0, C equal to 0. Now we do the similar thing as we did here. What we have now is we have this cylinder. Now I'll restrict, no, not restrict. I'll use this cylinder and I'll take this Z action on this R, along this R, so that I have this cylinder and I get a solid torus. So what I'm doing is I'm identifying points here. So this is x3 equal to y3 equal to 1, and this is y3 equal to 0. So I identified these points. How so x y1 y2 1 is identified with y1 y2 0. So this identification gives a solid torus. And what will be the foliation that will be induced on this solid torus from this? And again, this induction, why we are getting a position on this solid torus is because this position is invariant in the vertical translation. If we take like we got the map, yeah. If we take some y3, if we translate y3 along
Leaves don't get. The leaves themselves are not there, of course.
no, invariant. Just position being invariant means leaves goes to leaves. It could go to different leaves. Just the leaves should go to leaves. Yeah, okay. So, how to see the induced foliation on this solid torus? So here, let's go to we start with this one paraboloid. So here is this one leaf. Now when it intersect here, we get a circle. And now this one, there is no space to go. These points are identified with these points. So this circle is identified with this one. And there was another leaf which was coming from here and which was passing through like this. Which was here, you can see it was another level curve. And now we get a different circle, which is again identified with here. And then again we'll get a leaf, right? This curve. But what's happening in the torus, solid torus, let me explain that. I'm just looking at the two-dimensional, right? So here is this circle. Here is this circle which is identified. So here I'm starting with the curve. So here was my leaf. Now this is continued. And I get this bigger circumference circle, which is again like going to continue and so on. So this leaf will keep going on, and what happens is towards infinity, or you can say asymptotic, it's accumulating on this boundary, on the torus. and which we already saw that it's a leaf of this torus. So each leaf is accumulating on this compact leaf, the compact leaf being this boundary, this torus. And also, it's different from the case of this foliation on torus, where leaves were immersed manifolds. These are not immersed manifolds. These are nice embedded ones. They are not closed embedded, closed embeddings, because they are kind of accumulating on this compact leaf, but they are embedded submanifolds. So they are nice submanifolds. And yeah, so having this foliation on the solid torus, we patch these two torus along the boundary, which is a torus. We get a foliation on of S3. Now, this is just a constructive foliation. It's just a constructive example. But as I said, it was proved later on that almost every, not almost every smooth foliation on S3 looks like this. They will have a component. There is a one leaf, exactly one leaf, which is compact. So homeomorphic, decomorphic to torus, and all other leaves will be copies of R. So yeah, each let's call this compact leaf as L. Each leaf L cap. Each leaf L other than L cap is a copy of R. So there is one compact leaf, and there are all these copies of R2, which are situated in the solid torus or S3 and accumulating on the compact leaf. And this behavior is true for all foliation, even for a larger class of manifolds.
Stitch out of two solid chloride.
Sorry.
Is anything you can stitch out of two solid chloride at the same time?
So I take the same foliation on both.
Yeah, that's what I'm saying. But you don't always get to see solid chloride.
So the way I'm stitching is what I described here. So the intersection of these two solid chloride is the torus.
I was just saying that, isn't it true that we can get other manifolds by trying to solid torus above their boundary, and so then individually each torus would still have this foliation. I'm just trying to see if other manifolds the same, because you're kind of doing it on the individual pieces. I was wondering if you can get a similar foliation in other things that can be built out of two solid chloride, which meet on this.
It's possible, because this result that every foliation looks like three foliation. It's not just for S3, it's for more bigger classes, but every simply connected three-dimensional. Exactly, three-dimensional. Or
when you say it's a copy of the red foliation,
yeah.
Do you mean that given two different foliations, there's a diffeomorphism of S3? So that if there's a leaf preserving diffeomorphism. So what do you mean by is a? I mean, if you take two a priori different foliations, what does it mean? One is the same as the other.
Okay, although in foliation terms, when we say two foliation are same, we do mean this, that one is induced from another through a diffeomorphism or something. But I don't know if reap or because this result that every foliation looks like reap foliation is by Novico. I don't know how he proved it, but maybe it's possible that the way he's thinking is this one, that there is a homeomorphism, diffeomorphism through S3. But what is known is that what it means by looks like reap foliation is that foliation, you take any two-dimensional foliation S3, there is exactly one compact leaf which is diffeomorphic to torus, and all other leaves are copies of R2 which are accumulating on this.
Okay, so that means what I'm conjecturing is a strong statement.
Yeah.
What you just meant was that that there is a non-compact leaf and there is a compact leaf.
Yeah.
And the compact leaf is at least homeomorphic to the
Yes. I mean, it's possible that the way they prove is what you are saying, but I'm not sure. But that would certainly imply this result.
This have this given and the complete. When we intersect on the solar plane, look, the solar is already on the boundary. So it's coming from the should ideally intersect the
They are asymptotically accumulating on the peak of this compact deep, which is chloride.
Are they accumulating transmission?
yeah. Why are they not hitting?
This is
That's
clear from
exactly
the
because
picture.
of the clear negative exponential.
Yeah.
So if you look at, so this is sort of the general idea of concave section, right? If you look at a disk with a donut, you can kind of do the arithmetic. And each circle of a leaf is actually going to increase at a certain rate, and you can compute the tangent vector of the leaf, and that the way the tangent vector along the tangent vector from the submanifold on each circle, the way it measures out, you know that it'll never hit the boundary. It'll never hit S1 cross S1 transpose.
That creates more problems, right? So on S1 projection, there will be leaves coming from let's say T1, going through S1 projection. There will also be leaves coming through T2. There will also be S1 projection.
So
They're not going to, they sort of just,
yeah,
Can we
this is
just-
solid progress. This
yeah, they're not going to, that's the thing, they're sort of asymptotic state.
That is exactly why we have an E to the negative
So
E to
think
the.
of the other copy as on the other side of the.
yeah. So the result that I was mentioning, this is true for
What about the boundary?
There's a leaf itself.
yeah, that's a so.
So we just declare it as a B, basically.
Yeah, I mean it's a level surface from the point C. Because this map has we can define on art not even just this one.
So these are still constructions, but like the original definition of the foliation for the maximal atlas, what are these there? So is it just maximal parts of those plates or what?
They define the equivalence class.
Yeah, exactly.
So before this, I told you I showed you how to get a foliation from submergence.
Yeah.
And these leaves are the level curves of submergence.
Yeah, but
I
if you
think
have
what
a
he's asking-
maximal atlas,
You actually forgot to say that a leaf is defined, a leaf through a point P is defined as the equivalence class of P.
Oh, I told
Right.
you.
You wrote the relation.
Yeah, no, I said
I think
leaves
you wrote,
as
you
yeah, okay, I said it verbally. Yeah, sorry, because the leaves are the equivalence classes.
I guess you also want to say that now you will think of them in terms of submersions and not go back to atlas.
Yeah. I mean, the next thing is exactly that. Because now, before this example, I showed submersion will induce a foliation. Now, I give another definition of foliation in terms of submersions. Submersion in the sense local submersions. So every foliation is locally given by submersion. Let me write this as definition 2, and with the time that I have that I might try to give give a sketch or an idea at least how to see these two definitions are equivalent of definitions of foliations. This is the original definition as definition 1. Three-dimensional foliation. M is defined defined by a maximum of pairs Fi. Where UI are open set in M, and the union of UI is M. It's a cover of it's an open cover of the manifold. We need a maximal collection of objects like this. And what are FIs? FIs on UI are A are submersions. So submersion on their image. So these are submersions such that if and there exists local singularities. TIJ, which is a map from FJ of I intersection. It's a local scene with decomposition. F5 Yeah. So a k-dimensional foliation we can also define as a collection of these pairs, a maximal collection. Maximal in the sense if any other pair UI Phi satisfies this condition, we add it to this collection. So we have such collection where UI is a cover, a set of UI is a cover of the manifold M, and we have submersions, local submersions on UI on, and how we get the position again is this condition. On the intersection, these submersions are related to local diffeomorphisms. Okay, so now some terminology like here these FIs, if you look at position definition in terms of submersions, these FIs they are called as distinguished maps of this map of the foliation. And in this case, the plaques of the foliation, because when I say foliation, what I really mean is a decomposition of the foliation. So the plaques in this definition are the level curves of these local submersions. And this condition ensures that on the intersection, these local these fibers actually overlap to give these global objects.
GID is just a diffeomorphism or local?
Globally.
So local diffeomorphism.
No, it's the domain where it's defined.
Yeah, it's already local.
Okay.
Right.
Yeah. Yeah. I was thinking without writing the domains, but now I have written the domains. It's different. Okay, let me quickly, maybe within 3-4 minutes, I will give you a sketch of how to go from one definition to another.
You can do it in the discussion session.
Okay, yeah, that's fine as well.
So another customer said that there's a single correlation between one of these stories. So then you should throw it like two-dimensionally. You have this right. Yeah. So, like in a circle, right? With another torus inside this. You can put the ring foliation here. Right? And then add foliation no, the outside is not a torus. Yeah. The torus, the outside is not a torus. But I will have this torus. So it's not a solid torus, it's just a torus. So I put a torus inside a torus.
So put a solid torus inside it, so take the core of the solid.
Yeah, exactly.
But the complement of that is.
That's not a torus. Yeah. It's a torus with a torus cap.
Yeah, but then that will have to have.
This sort of foliation thing where you're instead of closing this in the big foliation, you're just sort of approaching the you go. They wouldn't be our copies of ours. Right, but then you get foliation, and you get this, and then put, on the complement you would put just a standard refoliation, and you have a foliation of S3 with two compacts. Right? So you could do the same thing here, so you can like find any number of compact leads.
It's just like it has to be finite.
I guess we have to be finite. I think that becomes like it says that there is at least one torus, and inside the torus there is the ring foliation. Maybe like outside you could have other things. Yeah. But there's at least one that has the ring foliation, that is a torus, and that has the ring foliation.
That corresponding
Or inside, yeah. So somewhere like once you go far enough, like this, the last one has to have those guys are copies of our tape. That's like, but these guys would be just cylinders.
So that doesn't have to be like a contact cavity anyway. Even Drake's name also associated with the effective field which comes from. And S3 has a contact structure because it's like strongest of contact.
Original question was
So it's like this.
Yeah, I think it's rare. Yeah, I always say real, but I know people say rare, and it's
Like I'm already,
so it is.
I heard the rev.
I don't even know where it is.
Yeah.
Also, one dimension, the Hawk federation, I mean, those are easy to construct, and one dimensional variations for S3, they're not, they're very, I mean, even these will give you very big.
So can we put on that one was
That one you just go down to an S2, and then you get you can do it in C2. You just go, you can have a map, you put S2 and you get these S1. But like if somebody gives you an S3 and says give a one foliation for it, it's not immediately obvious that it's S2. Because everybody tends to draw the longitudes, and it's not immediately obvious that I have one.
and the idea was
Right, I wanted to know about higher dimensions. Is codimension K obvious? Is it all?
There is a distribution that there is a foliation. But because on S2 we do not have a straight distribution.
But it has to be integral, right? I mean the distribution is so it's always integral. But if it's codimension K, but once you have a foliation, both the dimension spaces gives you a distribution. Why is it one direction? Like once you have a foliation, the dimension spaces will give you an integral. Yeah.
We have a distribution which is integral.
Yeah.
It's the other side which is through by being from this theorem.
Ah, right.
if you have a distribution, then you can have distribution.
but actually one distribution is trivial, so it's always integral one distribution. We also have some nice condition minus one distribution. Codimension one distribution, which is given by one closed one.
Oh, so
One
you're saying
right,
one
right.
distribution is a
Closed one
problem.
from our special case. Just
One-
gives us.
One distribution is a problem because you will have zeros on certain spheres. Your vector field will have to have zero. That's the reason why you can't have it on S2, right? Because your vector field will have to have a zero and therefore you cannot have a one.
So there are similar conditions there.
Right, right.
In this case, this
Or just,
circles.
yeah.
These are the spheres.
correct.
Yeah.
So that's the
nodes,
proof of that statement you made, right? No one foliation for S2. You can do it like that.
Oh. Okay.
Okay, nice, yeah.